Next we have exercise 8. Here there are two parts. In both the parts we have a triangular matrix. In the first part, A is a triangular matrix and we have to prove that the entries which appear on the main diagonal, the leading diagonal of A, are exactly the characteristic roots of A. And in part B, we have to prove that if all these leading diagonal entries are 0, then A is nilpotent. And we have actually solved both these parts before. For part A, you see exercise 28 of section 6.3. So it is that third section which involves matrices. And for part B, you see exercise 30 of that same section. Okay, so that means it's done for us already. Next we have exercise 10. Here A is an invertible matrix. Then we have to prove that the transpose of its inverse is equal to the inverse of its transpose. So let's see the solution. The solution is pretty easy. Here we just use lemma 685, which has properties of transpose. So one of those properties, namely the third one, tells us that if we take the product of the transposes of two matrices, then that equals the transpose of their product. We just change the order. So by that result, A inverse transpose times A transpose would be equal to the transpose of the product of A and A inverse. So we change the order. First we write A and then we write A inverse. But A inverse is the identity matrix whose transpose is itself. In a similar manner, if you instead consider this product, A transpose times A inverse transpose, again you get the transpose of the product, but the order gets changed. A inverse comes first and then A. So again you get identity matrix transpose, which is identity matrix. So these two equations means you then have one of them is this times this equals the identity matrix, and the other one is this times this equals the identity matrix. These two equations tell us, first of all, that just like A transpose is also invertible. And the second thing is that its inverse is nothing but this. Because the inverse of a matrix, whenever it exists, is unique. Okay, so that's how we have this solution. Next we have 12. Here there are two square matrices A and B which are symmetric. That is given. Okay, that's not changing. A and B are already symmetric. Under this condition, we have to prove that their product AB is also symmetric if and only if A and B commute with each other. So let's see the solution. So this is the solution. Let us first assume that AB is symmetric. Then AB will be equal to its own transpose, AB transpose. But then you apply that property of transposes, that you can apply the transpose on each of the matrices in the product, only the order changes. So it becomes B prime A prime, but it's already given that A and B are symmetric. So B transpose is equal to B and A transpose is equal to A. So you have ended up proving that AB is equal to BA, that is A and B commute with each other. So that is one half of the claim. And the second half is this, where we assume that A and B commute with each other. Now we have to prove that AB is symmetric. So to prove that AB is symmetric, we have to show that its transpose is itself. So let us calculate its transpose. We immediately use this fact that in place of AB we can write BA, and then we apply the transpose on each of these matrices. So the order gets changed. Here we have BA, here we will have A transpose, B transpose. But then again you use the fact that A and B are symmetric. So A transpose is A and B transpose is B. So that way we see that the transpose of AB is equal to AB itself. That's why AB is symmetric. So that is the solution. And let's end the video here itself. And tomorrow again we have our analysis. And tomorrow we are going to start the results on metric spaces. We have already gone through the examples. So tomorrow we will see what convergence of a sequence in a metric space means, and then the other results that come after that. So that's it for tonight. See you tomorrow with that. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.